Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 6, Lesson 10 on the symmetries of quadrilaterals. This is our last topic in Unit 6, which has been devoted to really looking at four-sided figures, right? Quadrilaterals. And today we're going to talk about the various symmetries of the special quadrilaterals that we've seen throughout this unit. You'll look at a few additional symmetries or a few additional quadrilaterals and their symmetries on the homework assignment for this lesson. But today we're going to really kind of get into all those special ones like parallelograms and rhombuses and rectangles and squares. So let's jump right into it and let's remind ourselves of what a symmetry is. Now, when a transformation is a rigid motion, we know that it maps a figure. The image produced is identical to the pre-image. But a special type of a rigid motion occurs when the figure is mapped onto itself. Okay? So recall from Unit 2, because we've already talked about symmetry once before. Let's take a look at its definition again. A symmetry is any rigid motion that maps a figure onto itself. In other words, after you have applied the rigid motion, the object is both identical to the original and in the same location. All right, so again, right, you've got these rigid motions, which are reflections, rotations, and translations, right? And whenever you do any one of those to a geometric figure, the figure that you end up having is identical to the original, but it could be in a different orientation, a different location, etc. A symmetry is one of those three that then literally, when you look at the final picture, it looks identical to the original picture. So let's begin by taking a look at symmetries of parallelograms. Exercise number 1. Given the general parallelogram ABCD shown below with diagonals intersecting at point E, answer the following questions. Letter A. What is true about the diagonals of every parallelogram? All right, this is critical, okay? Because it'll help us understand the one and only type of symmetry that generic parallelograms have. Pause the video now and tell me what's true about the diagonals of every parallelogram. Well, hopefully you said they bisect each other. I'm really hoping you didn't say that they were congruent. Right? They bisect each other. Generally speaking, in most parallelograms, one diagonal is longer than the other diagonal. But what is always true is that they bisect each other. Now let's take a look at letter B. Describe the rotational symmetry that every parallelogram must have based on A. Verify using tracing paper. All right, so what kind of rotational symmetry must every parallelogram have based on the fact that the diagonals bisect each other? Pause the video now and see if you can figure this out. Well, keep in mind what it means for diagonals or for two line segments to bisect each other. What that means on the diagram, right, is that AE would be congruent to CE and DE would be congruent to BE. Now, what that really means, because A, E, and C are collinear and B, E, and D are collinear, is that if I rotate this entire figure by 180 degrees about point E, then A will end up mapping to C, C will end up mapping to A, B will map to D, and D will map to B, right? So it will get mapped onto itself. All right, let me move this over here. That's for verification purposes in just a moment, but 180 degree rotational symmetry about point E. And I can't get enough of verifying this with tracing paper. Of course, this isn't tracing paper, but the same idea. If I just overlap this like that, okay? And if I now take that figure and I start to rotate it, right, and I rotate it around 180 degrees, it ends up being mapped onto itself, right? Isn't that great? That 180 degrees, I can do it again, right? And it maps onto itself. There's no other angle except for 180 and of course any integer multiple of 180, so 360, etc., right? But it'll have a 180-degree rotational symmetry about point E. Now, one thing before we move on, keep in mind that every now special type of parallelogram, and those are the rectangle, the rhombus, and the square, all three of those then inherit this particular rotational symmetry because they're all parallelograms. Cool, but that's it. There's nothing more. There's no lines of reflective symmetry. There's no other angles of reflective symmetry. 180-degree rotational symmetry about the point where the two diagonals intersect, and there's one specific reason for that, because they bisect each other. All right, so now let's talk about the symmetry of a rhombus. Now, all parallelograms will have 180-degree rotational symmetry about the point where their diagonals intersect. This includes all special parallelograms. Additional specific properties of a special type will then give rise to other types of symmetry. And we'll start off with the rhombus. So again, right, because these other figures, the rhombus, the rectangle, and square, have additional properties besides, the ones that parallelograms have anyway, they will then pick up other types of symmetry. And I love the symmetry of the rhombus. Let's take a look at exercise number 2. Rhombus PQRS is shown below with diagonals intersecting at point T. Answer the following questions. Letter A, what is true about the diagonals of all rhombuses? All right, pause the video now and see if you can write something down. Well, there's two things that are true about them. Number one, they bisect each other because a rhombus is a parallelogram. And number two, they're perpendicular to each other. Now that's very specific to the rhombus itself. And therefore, what's true about the diagonals of all rhombuses? They are each other's perpendicular bisectors. Now again, what really makes the rhombus stand out as opposed to a generic parallelogram is the fact that the diagonals are perpendicular to each other. The bisector part comes from the fact that it's a parallelogram in the first place. Now let's take a look at letter B. What kind of reflective symmetries does A give rise to? Be specific. Reflective symmetries now, not rotational, but reflective, right? Now again, right, reflections across lines are all about, right, perpendicular bisectors. So pause the video now and see if you can explain what kind of reflective symmetries or reflective lines of symmetry that we get based on letter A. All right, well, it's plain and simple. Both diagonals will be lines of reflection or reflective symmetry in a rhombus, right? So both diagonals will be lines of reflective symmetry, right? And it's so cool. It makes all the sense in the world, right? Just think about this for a second and then we'll kind of visualize it down here, right? If we've got, let's say, just the fact that SQ is the perpendicular bisector of PR, right? Then what will happen is when we reflect a rhombus across SQ, point P will be mapped to point R, and point R will then be mapped to point P. Of course, point S and point Q will just get mapped to each other because they are on the line of reflection. And then you can make the same argument if we then reflected it across diagonal PR. Q would get mapped onto S, S would get mapped onto Q, right? And P and R would stay in the same place. Now again, right, that's not generally true of most parallelograms because most parallelograms don't have diagonals that are perpendicular to one another. But rhombuses do, right? So let's take a look, letter C. Test these reflective symmetries using tracing paper. Also verify that the 180-degree rotational symmetry about point T is valid, as it should be for all parallelograms. So this is really cool. Let's first take a look at the reflective symmetry across the longer diagonal of SQ, right? So if I take this particular figure and I move it so that I can actually see, right? And I do a flip up, down. There we go. We see that that red sort of triangle flipped from the top to the bottom, and the blue triangle flipped from the bottom to the top. By the way, let me take a look at that 180-degree rotational symmetry while I'm right here. Right? If I rotate it by 180 degrees, about its center point, it then maps back onto itself. Again, that would have been true of any parallelogram, but certainly true of this rhombus. Likewise now, I can show that other diagonal is a line of reflective symmetry. If I bring this one up like this, lie it on top of my figure, and again, you can do this with tracing paper by just sort of tracing out the figure and the diagonal and then flipping it. But if I do this, now again, watch where the red goes versus the blue. If I now flip, come on, there we go, flip left, right. My board's not happy with me today, come on. There it goes. It took a little while, but it finally did it. Notice the blue went from up here down to here, and this went from down here to up here. All right, so those diagonals, right, are lines of reflective symmetry. Generally they aren't, right? The only reason they are in this case is because they are each other's perpendicular bisectors. All right, but the last little piece is important, letter D. Explain why a rhombus in general does not need to have rotational symmetry about point T by 90 degrees. Verify that it does not using tracing paper. So again, right, you might think, all right, like I get the 180-degree rotational symmetry, right? All parallelograms have that. But given that the diagonals are perpendicular to each other, you might suspect that if I just rotate this by 90 degrees about point T, it will end up mapping onto itself. Well, just for a moment, take a look at what happens when you attempt to do that, okay? If I rotate this 90 degrees, it ends up being right there, which is a cool looking picture, granted, okay, it's cool, but certainly it didn't map onto itself. So why was that? Why didn't it map onto itself when we rotated at 90 degrees, but it does when we rotate at 180 degrees, right? It doesn't when we rotate at 90, but does when we rotate at 180. Pause the video now and see if you can explain why that's true. Well, they simply won't map onto themselves because the diagonals aren't the same length. And I'm going to say they are not generally, because you can have some rhombuses where the diagonals are the same length, but the diagonals are not generally the same length. And keep in mind, right, the whole idea of a rotation is that we're moving a point along a circle, right? And so point P, right, when it's getting rotated, is moving along a circle that has a radius that's this length, whereas point Q is rotating along a circle that has this length. And because TQ isn't the same length as TP, there's absolutely no way that Q will ever get mapped to where point P is. All right? Of course, if the diagonals did have the same length and were perpendicular to each other, then it would map onto it. But in general, in rhombuses, that's not the case. All right, let's go on now and talk about my favorite figure, the rectangle. That was a little bit of a sarcasm. Even though the rectangle is simple, it's actually a little bit complicated to discuss its symmetry. Our next figure to analyze is the rectangle. Although the lines of symmetry for a rectangle seem obvious, and they really do, we want to be able to properly describe them and justify why they must be lines of symmetry. So let's get into that. It's that justification that's a little bit tricky. Exercise number 3. In the diagram shown below, KLMN is a rectangle. Points P and Q are the midpoints of sides KL and MN respectively. Answer the following questions. Letter A. Explain why quadrilateral PLMQ must be a parallelogram. All right, now this is a little bit tricky. Again, all we know at this point is that the overall figure is a rectangle, and point P and point Q are the midpoints of those two sides. I'd like you to try to explain why PLMQ must be a parallelogram. I know, you're probably thinking it's not just a parallelogram, it's also a rectangle all by itself. We'll get to that eventually, but why does it have to be a parallelogram? Pause the video now and see if you can explain that. All right, well, because it's a rectangle, it's a parallelogram, number 1, right? So KLMN is a parallelogram. So not PLMQ, but just KLMN is a parallelogram because it's a rectangle, right? But that means two things, right? That means that KL is parallel to NM and KL is congruent to MN. Now you're probably saying to yourself, okay, well, great, but that doesn't help me with PLMQ, right? But if KL is parallel to NM, that means that PL must be parallel to QM. Right? PL must be parallel to QM. And I'm running out of room here, so I might not be able to get all my reasoning in, but KL is the same length as NM. P and Q are midpoints of those two sides, so PL must be the same length as QM. Right? And there it is. Right? We had this condition that said if we have a figure that has a pair of sides that is both parallel and the same length, it must be a parallelogram, right? I think that was sufficient condition number 2 for what makes something a parallelogram, right? So I know that these two sides, PL and QM, are the same length because they're half of two sides that are the same length. And I know that they must be parallel to themselves or to each other because they are parts of two segments that are parallel. All right, so PLMQ is a parallelogram. Awesome. All right. Second piece, letter B. Explain why, given A, PQ must be perpendicular to both KL and MN. So remember, all we know about line PQ is that it goes through the midpoints of this and this side. So why would it have to then by default be perpendicular to those two sides? Again, we now know PLMQ is a parallelogram. Pause the video and see if you can figure out why PQ must be perpendicular to those two sides. Well, keep in mind, PLMQ is a parallelogram, right? And in a parallelogram, opposite angles are congruent, okay? And since opposite angles are congruent in a parallelogram, that must be a 90 degree and that must be a 90 degree. And therefore, PQ must be perpendicular to both KL and MN. Let's get that down, right? PLMQ is a parallelogram. And opposite angles in a parallelogram are congruent. So angle LPQ and angle MQP are right angles, which proves PQ is perpendicular to KL and MN. Now, why was that so important, right? That line was not just going through the midpoints of those two sides, but also was perpendicular to those two sides. Well, that gets then into letter C. Why must PQ be a line of reflective symmetry for rectangle KLMN? All right, well, see if you can write something down. It's very simple, right? PQ is the perpendicular bisector of both KL and NM, right? PQ is the perpendicular bisector, and that's what it's all about for reflective lines of symmetry. Perpendicular bisector of KL and NM, right? And so if we were to reflect the rectangle across that, L would get mapped to K would get mapped to L, M would get mapped to N, and N would get mapped to M, and therefore the quadrilateral would be mapped onto itself. Okay? Simple enough. And now, of course, we can get our final line of symmetry for the rectangle, letter D. Sketch the other line of reflective symmetry for the rectangle and give a description of it below. All right, well, why don't you go ahead and do that? Well, first, let's describe what it has to be. It has to be sort of the equivalent of this line, except going horizontally, right? So what I'm really doing is I'm going to draw a line, and you can have it dashed or solid, doesn't really matter, right? But it will be a line that passes through the midpoints of sides KN and LM. All right. And again, you probably way back as early as maybe even 4th grade were drawing these two lines of symmetry for a rectangle. But now you have all the tools you need to explain why they are lines of symmetry. And importantly, you also have the tools now to understand why other lines are not lines of symmetry. And let's take a look at that final issue in letter E. Finally, why are the diagonals of a rectangle generally not lines of reflection for the figure? Draw them in to understand. All right? So letter E, right? Here we've got our rectangle with our original line. Draw those diagonals in and think to yourself, why wouldn't those be lines of reflective symmetry like they were for the rhombus, by the way? They were for the rhombus, but in general, for a rectangle, they aren't. Pause the video now, draw those diagonals in, and see if you can give an explanation for why they won't be lines of symmetry in general. All right, well, it's pretty simple. If I bring this up here, right, so that I have my diagonals drawn in, okay, the real issue was, why was it that for a rhombus, they were lines of symmetry? Well, for a rhombus, they were lines of symmetry because they were perpendicular bisectors of one another. Now, certainly the diagonals of a rectangle are bisectors of one another, but in general, the diagonals of a rectangle are not perpendicular to each other. The diagonals of a rectangle are not generally perpendicular. All right. And it's really cool because it can be difficult, right? It's easy to be like, well, sure, maybe if I flipped it across that, it would map onto itself. Watch what happens when we do that. If I flip this thing over the one that goes from the bottom left to the upper right, I get that. That did not map onto itself, right? And again, right, that diagonal stayed in the same place as all lines of reflection do when you do that, but that thing definitely did not map onto itself. And it's really quite simple. All right, let me flip it back. Right? The only way that ever happens, right, is if the lines are perpendicular bisectors of each other. Because if I just take this single point, right, to reflect it across that other diagonal, I have to go perpendicular to the diagonal because that's what a reflection is. A reflection always flips a point across the line of reflection in a perpendicular direction to the line of reflection. So, you know, if the two diagonals are perpendicular to each other, then of course you just reflect it across and it hits on the other vertex, but not in the case of a general rectangle. Now, I keep having to say in general, right? I can't actually say, you know, will the lines of reflection for a rectangle be, you know, will the diagonals be, you know, lines of reflection for a rectangle? Because the answer to that question is sometimes, right? Because sometimes for a rectangle, the diagonals could be perpendicular to each other, in which case they would be lines of reflective symmetry. But if that was the case, the rectangle would also be a square. Our final figure is the square, and it has the most types of symmetry because of how many special types of parallelograms it can be classified as. Now, back in Unit 2, when we looked at the symmetries of regular polygons, we actually did already study the symmetries of a square. But let's now really kind of list them all out. Exercise number 4. Square ABCD is shown along with various lines and segments drawn. For each figure below, describe the symmetries the square has because it falls into each particular category. All right? So what I want you to do is, based on this picture, I want you to tell me what kind of symmetry does the square have because it's a parallelogram. Then tell me what kind of symmetries the square has because it's a rhombus. Then tell me what kind of symmetries it has because it's a rectangle. Pause the video now and go ahead and do that. All right, well, because it's a parallelogram, it only gets one type of symmetry, which is 180 degrees rotation about point E. That's it. That's all I get because it is a parallelogram. So if I took this thing and I rotated it 180 degrees about point E, B would map to D, D would map to B, A and C would map to each other. Done. Now, because it's a rhombus, right, I know the diagonals are perpendicular bisectors of each other. So this would be reflective symmetry. And you could say reflective symmetry across its diagonals, or I'll actually name them here since they are labeled, across AC and BD. So we get reflective symmetry across AC and BD. And finally, for the rectangle, which we just looked at, of course, it gets reflective symmetry across line M and line N. All right, and of course you could always describe those as lines that pass through the midpoints of two opposite sides. Now, there is one last symmetry that the square gets, letter B. There's one additional type of rotational symmetry that the square has that's not listed above. It comes from the fact that a square is both a rectangle and a rhombus. What is it, and explain why it occurs? All right. Pause the video now and see if you can figure out this final type of rotational symmetry that the square gets. All right, well, it's now going to have 90-degree rotational symmetry about point E. 90 degrees rotational symmetry about point E. And we'll talk about why that is in just a moment, but let's actually take a look at it. Let's visualize it, because it is, to me, pretty darn cool, right? If I take my square and I now just rotate it by 90 degrees, it lands on itself. Then another 90 degrees for a total of 180, it lands on itself. Another 90 degrees for a total of 270, it lands on itself. And another 90 degrees for a total of 360, it lands on itself. So when I say 90 degrees rotational symmetry, I'm talking about 90, 180, 270, 360, okay? Now, why does it have it, right? Well, it has it for two reasons. One, because the diagonals are perpendicular to each other, and two, because the diagonals are the same length, right? And both of those have to be true to get that 90 degrees rotational symmetry, right? And this is because diagonals are perpendicular and the same length. And it's kind of cool, right? The fact that they're perpendicular comes from the fact that a square is also a rhombus, and the fact that they're the same length comes from the fact that a square is a rectangle. All right, put those two together and you get this additional type of rotational symmetry that doesn't occur in any of the other types of quadrilaterals. All right, let's wrap this up. So what we did today is we reviewed what a symmetry was, right? It's a rigid motion, and for us, those are always going to be line reflections and rotations that will map a figure onto itself. In other words, after you've performed this particular rigid motion, the image that you have is identical to the pre-image. Now, there's a variety of different types of symmetries. For parallelograms, just that 180 degree rotational symmetry about the intersection point of its diagonals. Whew, that's wordy. For a rhombus, it's that reflective symmetry across its diagonals. And for rectangles, it's that reflective symmetry across the lines that pass through the midpoints of its opposite sides. The square, being the most complicated of them all, gets all of those symmetries along with that 90 degree rotational symmetry that we saw at the end. Symmetry is a fascinating topic, and I hope that you notice it more and more when you look at artwork, engineering design, and things like that. Think about different ways that you can rotate figures, reflect them, maybe even translate them if you see sort of tiled patterns here and there, because it's rather cool. Symmetry is something that's inherently appealing to the human eye, and it's also very mathematical. All right, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.